All right, let's get into number 3 now. So this is another multi-part problem. So we'll start as always by talking about the system and the problem statement and setting up the assumptions before we jump into each of the solutions. So starting with the problem statement, it says a vapor compression refrigeration system using R134A within the vapor compression cycle has the following conditions known for R134A. The compressor inlet is superheated vapor with P1 equal to 1 bar and T1 equal to negative 7.37 degrees Celsius. So this is the state 1 down here that they're talking about. They give us the temperature and the pressure, and they tell us that this is superheated vapor. So I'm just going to write that right next to the state right here so that we remember it. I'll write it next to the table as well. We're at superheated vapor phase. Then it says that the compressor exit pressure, P2, is equal to 7 bar. So it tells us that P2 here is 7 bar, or 700 kilopascals. But that's all we have about that state so far. Then the condenser exit is saturated liquid, which would be this state right here at state 3. We would be in this saturated liquid phase. So I'll write saturated liquid. And the mass flow rate is 0.05 kilograms per second. So I'll write that on the side here as well, just so we don't forget. M dot equals 0.05 kilograms per second. And that's going to be our mass flow rate everywhere, because all of the mass flow rate that goes into the compressor comes out of it, and that same amount goes into the condenser and out of it, into the turbine, out of it, and into the evaporator. So this will be our constant mass flow rate throughout each of the components here. The turbine, it tells us, is adiabatic. So over the turbine, we don't have to worry about any heat transfer terms. Our Q is going to be equal to 0. And its isentropic efficiency needs to be determined. The compressor is reversible, but not adiabatic. So over the compressor, since it's reversible, that means that our entropy generation term, sigma C, is going to be equal to 0, but our heat transfer term, QC, is not going to be equal to 0 because it is not adiabatic. And it undergoes a polytropic process with PV equal to a constant. So that means that our P times V at state 1, P1 V1, is going to be equal to our P2 V2. That's what that polytropic process with constant PV means. And if we look at our table, we already have some information about P1, V1, and P2. So we know that we can really easily find V2 here, and that will help us later on in the problem. Assume that the pressure drops in the evaporator and the condenser are negligible. So that means that the pressure at state 2 should be equal to state 3 because there's no drop across the condenser. We see that in our table as well. Those pressures are equal. And same thing in the evaporator. P4 should equal P1, and we do see that they are both at 1 bar. Some of the property data is provided in the table below. We already see that. We have this table here. And so let's jump into the system and draw out the energy and mass interactions. So they give us a space to do this here on the next page. Sometimes when we're looking at cycles, it can be useful to draw our system around the whole thing and just look at the net heat transfer and work terms going in and out of the cycle. But here, we're missing a lot of data, and they're asking us to do some analysis over these different components here. So I'm going to draw individual boundaries of the system around each of the components here. So I will draw a boundary around the turbine, around the evaporator, around the compressor, and around the condenser. Because we're basically just going to treat each of them like their own control volume and apply our fundamental laws across these devices on their own. Then we can put that information together to look at the cycle as a whole. So for mass interactions, remember we only have one mass flow rate, so that m dot is just going to be the same throughout the entire cycle. Each component is going to have the same mass flow rate going into it and coming out of it. So I'll just write that for all of the components to be thorough here. but that will be the same mass flow rate for all of them. Now let's talk about heat transfer terms. So it tells us that our turbine is adiabatic here, which means that the heat transfer here is going to be equal to 0, but the compressor is not adiabatic, it tells us. So we're going to have some heat transfer term coming out of the compressor here. So I'll call that Q dot from 1 to 2 for the rate of heat transfer from 1 to 2 going out of the compressor. And then we know that our evaporator and condenser devices will have heat transfer as well. In a vapor compression cycle, we have heat transfer going into the evaporator. So I'll call that Q dot 4 to 1. And then we have heat transfer coming out of the condenser, Q dot 2 to 3. Right, because the goal of this vapor compression cycle is to have some cold reservoir down here, and we want to remove heat from that cold reservoir and move it out into a hot reservoir. So in order to do that, we need to put some work into our compressor to make the system run, but that's the goal of the evaporator, is to remove heat from that cold reservoir, and the goal of the condenser is to reject that heat out to a hot reservoir. Then for our work terms, since we don't have any pressure drops across these components, we usually consider condensers and evaporators as no work devices, so we don't have to worry about work for either of these. But for our turbine and our compressor, we do have to worry about the work. So turbine is going to generate some work. I'll call that W dot from 3 to 4. And we're able to put some of that work back into the compressor and recover some work. But the compressor needs to be powered, so it's going to have its own W dot term from 1 to 2. And note that these terms are not going to be equal because we're going to need more work here for the compressor than the turbine is able to give. But we can still write these terms independently, and we'll probably have to find them throughout this problem. So this is all the mass and energy interactions that we have here. So we can make some assumptions and then move on to the solution. So for cycle problems, we usually treat them as steady state, steady flow problems. So I'm going to write SSSF for steady state, steady flow. We treat them as steady and nothing is changing over time. So we can eliminate all of the time-dependent terms in our fundamental laws. Then some of the assumptions they give us directly, like that our turbine is adiabatic. So I'm going to say that the heat transfer from 3 to 4 is equal to 0 because that component is adiabatic. Additionally, our evaporator and condenser terms, like we talked about, are not going to have any work. So I will just write the work from 2 to 3 is going to be equal to the work from 4 to 1, which is just going to be equal to 0, because these are no work devices. We can also neglect any changes in kinetic and potential energy. So I'm going to write delta KE equals delta PE, which equals 0, because they don't give us any information about those terms. And lastly, remember that it tells us that our compressor is reversible. So for any reversible device, we know that our entropy generation term, sigma, is going to be equal to 0 because this compressor is reversible. So that's all we need for now for assumptions. So let's move on to our solution for part A. All right, on to part A. We are asked to determine the temperature at state 2, T2, and to report our answer in degrees Celsius. So we're trying to find this temperature here that we are not initially given in the table, but what we are given is that we have a polytropic process with PV equal to a constant across the compressor. So that means that our P1 times our V1 is going to be equal to our P2 times our V2 across the compressor. And so if we look at our table, we already have information for P1, V1, and P2. So we can just use that to solve for our specific volume at state 2. And once we have specific volume at state 2, we can use that and our pressure in order to find the temperature at state 2. So that's our approach. We will just use this polytropic process relationship and solve for a specific volume at state 2. So writing that out here, again, we'll see that P1 times V1 is equal to P2 times V2. And so if we want to solve for this V2, we can just move pressure over to the other side here and rearrange to see that V2 is equal to V1 times the ratio of P1 over P2. So all of these values, again, we have in our table. V1 is equal to 0.20977 meters cubed per kilogram. And the pressure is 100 kilopascals at state 1, and then it increases to 700 kPa at state 2. So if we just fill in those values, we'll get V2 is equal to 0.20977 meters cubed per kilogram times P1 is 100 kPa divided by 700 kPa. And so these units will cancel out. We'll be left with just units of specific volume, and we will find that V2 should be equal to 0.029967 meters cubed per kilogram. So again, this is our specific volume at state 2, and we have our pressure at state 2, so we can use that information to find the specific volume, or to find the temperature at state 2. So if we scroll up and we look at our saturation tables, these are our SLVM tables for R134A. So we can compare the value for a specific volume that we got, which was, again, V2 equals 0.029967 meters cubed per kilogram, and compare that to the values that we see here in the table. So the specific volume for a liquid phase is really low, and the specific volume for the vapor phase is just slightly lower than the value that we got here. So we see that our V2 is outside the range of our SLVM tables, so we can't use our SLVM tables. Instead, we have to go to our superheated vapor tables, which we have right here. So we're going to be in the superheated vapor range, and we see that for a pressure of 7 bar, we have a value for specific volume right here that almost matches identically what we got for our value. So we can say that that's close enough, and our temperature is just going to be equal to 30 degrees C. So again, this is basically the volume value that we got for V2, and so this will be our value that we get for temperature of T2. And so I'll just write that down here. We found that from the superheated vapor tables, T2 should be equal to 30 degrees Celsius. So that will be our final answer here. All right, let's move on to part B now, which says calculate the power required by the compressor. And they want us to report our answer in kilowatts. So if we scroll down to our schematic, the term that we're really after here is this work from 1 to 2, this power input that we are putting into the compressor. So your first thought might be to apply first law over the whole compressor here, which is what we would usually do for a cycle problem. But here, the issue is we are trying to solve for this unknown work from 1 to 2, but they tell us that this compressor is adiabatic, which means that we also have an unknown heat transfer term. So if we tried to apply first law here, we would have two unknowns with one equation, and so we can't use that approach to solve for this work term. The alternative that we can do is we can use our boundary work equation because we're given that this is a polytropic process. So that's what we're going to do, and that's the same approach that we used for the last part of the problem to find that specific volume. We use this PV equal to a constant relationship. So we can use that again with our boundary work equation, which is our work is equal to the integral of P with respect to volume. So that's the approach we're going to use. Let's scroll down real quick to the equation sheet, just in case you forgot where that equation is at, but this is the equation we're going to use. Boundary work equals the integral of P dV. And we can use it because we can use our PV equals constant equation to get P as a function of V if we just move V over to the other side. And then we can plug that into this P here as a function of V. So we'll go through all of those details here. I'll write it in the equation section first. We can find this work from 1 to 2 as the integral of P dV. So now let's start writing it out in our solution section. Work from 1 to 2 is going to be equal to the integral from V1 to V2 of P with respect to V. And in this case, I'm writing it as specific work. So this is a lowercase w here with respect to specific volume. And at the end, we can get the total work by multiplying by our m dot term that we are given. But for now, let's just focus on the specific work here. And so like we said, we have this equation PV is equal to a constant. I'll just call that constant C for now. And we can actually evaluate this constant by just picking a state and taking the pressure and specific volume from that state. So if we take, state 1, we can just do P1 times V1 is going to be equal to that constant. And then we can use that in our equation. So let's just do that. We'll set this constant equal to P1 times V1. And we just have these terms from our table. P1 is 100 kPa, and V1 is 0.20977 meters cubed per kilogram. This is going to be equal to 100 kPa times 0.20977 meters cubed per kilogram. So if we plug this in, our constant C should evaluate to 20.977. And now these units here are going to be kPa times meters cubed per kilogram times meters cubed per kilogram. And here, I think it's useful to just simplify out our units right now because that's going to be useful for us later. I'll just do this in red here. But kPa here is, we can write this also as kilonewtons per meter squared. And so if we do that, then our meters squared cancels with this meters cubed. And so then we get kilonewtons times meters divided by kilograms. And then also we can realize that kilonewton times meters is kilojoules. So then these units simplify to kilojoules per kilogram, which is our units for specific work. So those will be the units of our constant here. And it's just useful to do that because we'll use that later on once we plug this in. And so now the step is to rearrange this equation here by moving volume over to the other side. And so I'll just write that out here. We say that P is equal to this constant divided by volume because now we can plug this pressure, this equation for pressure, into our PdV equation since it has a volume term in it. So let's write that out. Now we will see that our work from 1 to 2 is equal to, again, subbing in our pressure here with this term, C over V, the integral from V1 to V2 of C over V dV. And then this C is a constant value, so we can just move that outside the integral. This is going to be equal to C times the integral from V1 to V2 of 1 over V dV. Remember the integral here of 1 over V dV is going to be equal to natural log of V. And then when we evaluate it from V2, from V1 to V2, we'll end up getting this final expression. This is going to be equal to C times the natural log of V2 over V1. So make sure you're comfortable with this integral. But this is the result that we get, and so we can just plug in our values now. C, like we said, is this, I'll go down to the next line here. Work from 1 to 2 is equal to, C is this 20.997 or 977, and we found that our units are actually kilojoules per kilogram for this. And then we multiply by natural log of V2 over V1. We have those values in our table. Well, we solved for V2, but that's 0.029966, and then this one is 0.20977. So that ratio is 0.02966 meters cubed per kilogram, all divided by 0.20977 meters cubed per kilogram. And so these units here will cancel out, and we'll just get the final units in the units for specific work that we expect. So that checks out there. And the final answer for the work from 1 to 2 is negative 40.82 kilojoules per kilogram. Okay, so this is the value for our specific work, but remember they wanted it in kilowatts, not kilojoules per kilogram. So we need to convert this kilojoules per kilogram to kilowatts, and the way that we can do that is multiplying by our mass flow rate. So our W dot from 1 to 2, this is our work rate, is going to be equal to our work from 1 to 2 times our M dot term, which is the same throughout the entire problem. And that was just given, well, first we'll plug in negative 40.82 kilojoules per kilogram. And then that is times our mass flow rate was given up here as 0.05 kilograms per second. 0.05 kilograms per second. So now we see that these kilograms cancel and we're left with kilojoules per second, which is our unit for kilowatts. And so the final answer here should come out to be negative 2.04 kilowatts. Kilojoules per second gives you kilowatts. So this will be our final answer here. And you can check the sign if you want. It makes sense that our sign is negative in this case because we're doing negative work by doing work on our compressor. We have to put work into this device in order to make it run. So this is our final answer, and this is the final work. Now let's move on to part C, which asks us to determine the isentropic efficiency of the turbine and report our answer in percentage. So if we look at our schematic, again, the isentropic efficiency of the turbine here, it really compares the actual work that we're getting out of the process to the theoretical isentropic work that we would be able to extract, this WS. And so we have that equation in the equation sheet. If you forget, it's down here in the efficiency section. Our efficiency for a turbine, again, is just equal to that actual work divided by the isentropic work. So we just need to solve for these two components, and we can do that using our first law equation up here. And the reason that we are able to use that equation here over the turbine and we weren't able to use it over the compressor is, remember, for the compressor we had two unknowns. We had our work term and our heat transfer term, and we didn't know either of these terms, so we couldn't use our first law equation. But here our turbine is adiabatic, like we said, so there's no heat transfer, and so we can just solve for the work because we have the rest of the components that we need right here with these enthalpy values. So let's apply first law over the turbine. And so if we do that, we can make our simplifications. First of all, it's steady state, steady flow. So this ddt term is going to go to 0 because all time derivatives go away for steady state problems. And then we neglect any changes in kinetic and potential energy. And we said that this is adiabatic, so then this heat transfer term goes to 0. And so we're left with just these three terms, this m dot in, h in, this m dot out, h out, and this work term. And we can divide all of these terms by our m dot here, because m dot in is just going to be equal to m dot out. So if we divide all of them by m dot, our final form here is going to be our specific work is equal to our enthalpy in minus our enthalpy out. So again, this is our equation for work over the turbine when it's adiabatic. And in this case, we have H3 will be our enthalpy in. This will be our H in for both cases. But then our actual work out is given as this state 4A. Our actual enthalpy out is this value right here. And then our isentropic enthalpy out is going to be this value right here at the 4S state. So we can just use these two values and this value in order to plug things in for the two different cases of actual versus isentropic. So I'll just write that out. So first we'll do our actual case. Our work actual, like we said, is going to be equal to H in, which is just H3, and then minus our H out, in this case, is H4 actual. And then on the other side, our isentropic work is just going to be equal to H3 is still our H in, but now H out is H4S. And so we can just use these two equations here that we have for our isentropic work and our actual work and just plug them into this equation that we have here for turbine efficiency. And when we do that, we see the efficiency over a turbine is equal to work actual here in the numerator, which is this H3 minus H4A, divided by our isentropic work, which is this H3 minus H4S. So if we just plug in our values here, again, we have all of these in the table up here. It's these three values right here. So plugging those in, we should get, I'll move down here, our turbine efficiency is equal to H3, which is 88.849 kilojoules per kilogram, minus H4A is 84.485 kilojoules per kilogram. And we divide all of this by, again, our H3 is 88.849 kilojoules per kilogram. And then our H4S is 81.576 kilojoules per kilogram. And so all the units here will just cancel out, and we will get our final value. I'll write it over here. Eta T is going to be equal to 0.60. And they ask for it in percentage, so we can just say that our turbine efficiency is going to be equal to 60%. So this will be our final answer for the turbine efficiency. Now on to part D, we are asked to determine the coefficient of performance for the whole refrigeration cycle. So when we're looking at performance parameters for the whole cycle, now we want to take a step back and look at our whole cycle as our system. And so we'll look at what's happening with the heat transfers across the boundary of the whole system and the net work term that we're putting in. So we have our equation down in the equation sheet. Let's go look at that for the COP of a refrigerator. It's right here, and it's defined as QC divided by our net work term. So we need to remember what these terms are. Let's scroll up to our system and look at what those terms are. And I think it helps to think about the goal of the cycle. So the goal of a refrigeration cycle is to have some sort of low temperature reservoir here that I'm drawing at this low temperature. And this would be like the inside of your refrigerator. And we want to keep this as cold as possible. So we want to remove as much heat as we can from it. So this Q from 4 to 1 is going to be equal to our QC because we are removing this heat from our low temperature reservoir. And this is the goal of our cycle, to maximize this QC term. So that's what appears in the numerator of our performance parameter. So the other one would be QH on the other side, but we don't even need it to calculate the COP. We just need this QC term and our net work term, which is going to be the sum of the magnitude of these two work components from our turbine and our compressor. So I will write our COP equation here in the equation section. I also added the equations that I forgot to write in during the last part. But again, our COP for refrigeration cycle is defined as our QC divided by our net work. And we take the magnitude of this. This should always be positive. So we just need to find all of these terms here, and then we'll be able to just plug them into our COP equation. We'll start with the net work, and remember how that's defined. Our net work here is going to be equal to the magnitude of the work that we get out of our turbine plus the work that we get out of our compressor. And here I say plus because we found our compressor work to be negative here because we're putting that work into the system. So we're really adding our compressor work, but it's like we're adding a negative value. So we're finding the difference between these two terms. So we can find each of those terms, and we actually found some of them previously in the problem. One comment here, I'm doing this in terms of specific work, and I'll do it in terms of specific heat transfer as well. But you can do the problem either way, because here you see in part B, we found our answer in kilowatts, for the total power that we're putting into the compressor. And you can do that if you want and use the power for the compressor and find the power of the turbine, and then you would find the total heat transfer rate. But here we can also just use our specific terms and just not worry about the m dot at all. So the work from the turbine, we found this in the last part of the problem we were solving for the isentropic efficiency, but I'll just write it out again to be thorough. This will be our actual work component that we're getting out of the turbine. So we found that to be H3 minus H4A for the actual enthalpy at state 4. And this was equal to 88.849 kilojoules per kilogram minus our H4A was 84.485 kilojoules per kilogram. And so this should be a positive 4.364 kilojoules per kilogram. So this will be our component that we get from the turbine. The compressor, we also found the specific compressor work when we were solving for the total power. So I'll just write that in. But we found that, again, using our PDV equation. We found work for the compressor is equal to the integral of PDV. The result that we got from that, just look back to part B if you forgot how we got that, but the work from the compressor was equal to a negative 40.82 kilojoules per kilogram. Right, that was the specific work. And so the net work, again, we can evaluate that by just taking the magnitude of these components together. Work net is going to be equal to the magnitude of our 4.364 kilojoules per kilogram plus our negative 40.82 kilojoules per kilogram. Right, this is this component here. And so the magnitude of that will turn out to be 36.4 0.456 kilojoules per kilogram. So here is our net work component, and that's what we'll use in our COP equation. So now we just need to find our QC. And we can do that by just applying first law over this evaporator. There's no work term, like we said. We said that our work term here is equal to 0. And so we can just apply first law. So let's scroll down to our equation sheet and see how we will do that over the evaporator. So again, we have steady state, steady flow. This term is going to go to 0. We're neglecting changes in kinetic and potential energy, so those terms go to 0, and then there's no work, so this term goes to 0 as well. And we can divide through every term by m dot because we're doing things in terms of specific quantities, and all of these are going to be the same. And so the final version that we get here is that our Q from 4 to 1 is going to be equal to H out minus H in, which is really going to be equal to H1, because this is our H out, minus H4A, because this is our H in. And so this is the version that we are going to use. I'll write it in the equations section. Q from 4 to 1 should be equal to H1 minus H4A. And we have those values again up here in the table. H1 is 249.62 and H4A is 84.485. Again, we want to use the actual component here. We only use this 4S component for the efficiency. But when we're dealing with the actual process, we want to use the actual term. So this is going to be our Q from 4 to 1, which is just our QC value, should be equal to H1 again minus H4A, which is equal to 249.62 kilojoules per kilogram minus our H4A, which is 84.485 kilojoules per kilogram. And so this will turn out to be QC is equal to 165.14 kilojoules per kilogram. So this is our QC. And again, we have our QC and our work net, so we can evaluate this equation here. So finally, our COP for the refrigeration cycle is just going to be equal to our QC divided by our work net, magnitude of this, which should be equal to 165.14 kilojoules per kilogram divided by our work net up here was 36.456 kilojoules per kilogram. Again, the units are going to cancel here, but even if you did it in terms of power and you did it in terms of kilowatts, the units would still cancel out here. And so we'll get our final answer. COP for the refrigeration cycle is equal to 4.53. So this should be our final answer for part D. So let's move on to the last part of the problem, which is part E, and that asks us to show the cycle on the TS diagram on the next page relative to the vapor dome and the relevant lines of constant pressure. Label the axes and the four states and indicate the process directions with arrows. And they give us the information for the critical temperature and pressure for R134A. So since we're going to be plotting a TS diagram here, we want to have all of the information for temperature and entropy before we start to go to that plot. So we need to fill in these gaps here. We're not worried about state 4s in this case because we're only going to be plotting the actual case, which is state 4a. But here on our chart, we're missing the temperature at 4a, the entropy at 4a, and the entropy at state 2. Some of this information we already know kind of easily, but some of it we need to do some more math to find it. Another useful thing that I've been doing throughout the problem is just writing here next to each state what phase we are in, whether we're in the superheated vapor, saturated liquid, or SLBM phase, because we need to draw everything relative to the vapor dome. So it's going to be very useful to understand where we are at in terms of the vapor dome and what phase we're in. So some of this we already know. This superheated vapor and saturated liquid was given to us in the problem statement. This one we found through our math. And we also know the phase at state 2 as well, because we found these quantities earlier in our problem using this superheated vapor chart. And so that makes it easy for us because we're given the pressure and temperature here. We're going to be in this region, so our entropy value is just going to be this value right here. And so we can just take it right off of the table. So I'll write it in our chart. This is going to be 0.93130. And I'll just write this in so we remember we'll be in the superheated vapor phase for this one as well. Okay, now let's focus on 4a because we just need to get this temperature and entropy value. And so remember, we are in the SLVM range at 1 bar, which we have this table here at the bottom to find the quantities for each of the properties here. So if we're in the saturation region with this saturated pressure, we have a given saturation temperature. We can see that right here in the table. For all of these quantities, it doesn't matter where we are relative to liquid and vapor, all of them will have the same pressure and temperature of 1 bar and negative 26.361. So I'll write that temperature in, negative 26.361 Celsius. And then we need to find the entropy. But we're in the SLVM region. We're somewhere in between liquid and vapor. We can tell because we have an enthalpy value here, 84.485, which is somewhere in between the enthalpy value for liquid and the enthalpy value for vapor. So we're somewhere in between, and we'll have some quality value here. So we need to find that quality value in order to be able to find the entropy value. So that's what we are going to do with our math here. Remember, in the equation sheet, we have an equation for quality right here where we can substitute z for any property. So here we can just plug in, well, first we'll need to use enthalpy to find the quality, and then we can use the quality to find entropy. So I'll write this equation down in our equation section. Here it's going to be, I'll just write z mix equals x zg plus 1 minus x times zf. And so again, we can use either enthalpy or entropy. So we'll use both here. So let's start with finding the quality, like we said. So our h at state 4a is going to be equal to, looking at this equation, our x at state 4a times times hg plus 1 minus x4a times hf. So these values here are known from this table up here. And this value we have in our table above, right here. And so we have all the information we need to solve for x. And we can rearrange this equation to solve for x. I think I did this in an earlier part of the problem, so you can go back and look how I do that if you want to see the math behind it. But the result that you will get is x4a is equal to h4a minus hf divided by hg minus hf. And we just get this by doing some algebra on this equation to rearrange for x. And so if we plug in our values here, again, we are given this H4A. Up here, it is 84.485. I'm not going to write out the units just to save space, but these will all have the same units of kilojoules per kilogram. 84.485 minus HF we have from the table right here is 17.298. Divided by Hg here is going to be this value from the table, 234.46. 234.46 minus HF, again, is going to be 17.298. So we will get X for A is equal to 0.309. Okay, so now we have this X value, and we can plug this into this equation here in order to solve for our entropy value. So now we're using this same equation, but we're going to use S instead of H. So if we write that out, we'll get here S for A is going to be equal to X for A times SG plus 1 minus X for A times SF. So subbing in our values here, we'll get S for A equals 0.309. Yeah, I'm not going to write the units just because I'm running out of space, but these values from the table, they would have units of, here is SF, it's kilojoules per kilogram Kelvin. So anyways, this, we're using SG first, which is 0.95188. That will be 0.95188 plus 1 minus 0.309 times SF, which is right here, this 0.07195. 0.07195. And so if we solve for this, I'll just write the results right here. S for A should be equal to 0.34, I'll call it 344 and just do some rounding, kilojoules per kilogram Kelvin. So now we have this information, we can solve for, we can plot our TS diagram because we have all of the temperature values and all of the entropy values. I'll just write this up in the equation section. Here they usually round to 5 digits, so I'll just do the answer that I got with 5 digits, 0.34385. Okay, so let's start to plot our points, and let's keep in mind this, the phase that we're going to be in for each of these processes. First, we'll have to draw a dome on this TS diagram because we will have, some dome. We're drawing everything relative to the vapor dome. I'll just write in temperature. We'll have in degrees C, entropy in kilojoules per kilogram Kelvin. And let's draw in our lines of constant pressure as well, because here we're only going to have 2 lines of constant pressure. We only have 2 different pressures that we have to worry about. That's 1 bar and 7 bar. So I'll just draw those in because we'll need to figure out where we are at relative to those quantities as well. I'll draw them here in blue. So we'll have one that's lower and one that's higher. I'll draw it just like this. Again, remember the iso bars go up and to the right. We'll have one that's lower and then one here that is higher. So this will be well, let's see. So the lower bar here is going to be the lower pressure. And so the lower pressure that we have is the pressure at state 1 and state 4A, and that is 1 bar. So P1 equals P4A, which equals 1 bar. And then the one above will be P2 equals P3, which equals 7 bar. Because this is the pressure that we have for state 2 and state 3, as we see here. And then we need to start to draw in our temperature and entropy values. First of all, we have two things here, either in the SLVM region at 1 bar or the saturated liquid region at 7 bar. And so these have saturation temperatures associated with those values. We can just draw those in. So we'll draw in our T3 here is going to be 26.713. So we know, we know that this temperature is going to be just right across from this saturation region right here. So, all right, T3 equals, they don't give us much space, so I'm going to round here, 26.7. Sorry, I'm kind of running out of space. And T4 will be this temperature, which is associated with the saturation region right here. So this is going to be T4 is equal to negative 26.4. Okay, and then let's fill in the other temperature values that we know. So, okay, again, we know that at state 3, where we just drew in that temperature, will be in the saturated liquid region. So that means that at state 3, I'm drawing here on the graph, we should be along this saturated liquid line. So we know state 3 is going to be right here, and then state 4 will be somewhere in the SLVM region here, and we just found the entropy, so we can place that point there. But state 1 and state 2, we are in the saturated vapor region. So we're somewhere out here, and we're going to go somewhere like this from one isobar to the other. So let's look at the temperature data that we have. At state 1, we are at a lower temperature than state 3, so we know that we are going up in temperature. And we are also at a higher entropy value at state 1 than we would be at in state 2. So that means we are going up and to the left because we are decreasing in entropy and increasing in temperature. And the temperature that we are given at state 1 is negative 7.37, which is somewhere in between this negative 26 and this positive 26 value. So maybe we'll be somewhere around here. So I'll just draw in that temperature somewhere around here. T1 is equal to, again, that's going to be a negative 7.4. And the entropy value associated with it, well, we can just basically trace this line across to plot our point somewhere right here, and then we will have an associated entropy value with it, S1. And I really don't have a lot of room here, but I will try my best. S1 is equal to 1.0109. 1.0109. Okay, now let's draw state 2. So the temperature for state 2 that we are given is 30 degrees Celsius, which is higher than this saturation temperature for this saturation region, which makes sense. So we'll just be kind of slightly above it. And remember, we are decreasing in entropy, so we want to be to the left of this point from state 1. So this point will be somewhere around here. We'll label these points. This one is 1, this one is 2, and the temperature associated with that value is going to be T2 equals 30 degrees Celsius. Okay, so we've drawn those points in. Again, we said state 3, we are along the saturated liquid line, which makes our plotting easier because this is the saturated liquid line right here. And so we'll be somewhere along that line, and we know that we are in the saturation region here because we're given that the pressure for state 3 is 7 bar and the temperature is 26.7. So we're just at this point right here along the saturated liquid line. This will be our state 3. Oops, I forgot to draw in my entropy value for state 2. So that will be, again here, I'll try to draw this in. S2 equals 0.93130. So 0.9313. And then our entropy at state 3, we just come down here. And so this value here will be S3 is equal to, from our table, we found that to be 0.3324. So this will be 0.3324. And then for the last point here, we know that we will be in the SLVM region because we said that will be somewhere in between, the saturated liquid and the saturated vapor phase. We know the quality here is 0.309 because we found that from an earlier part of our problem. But the best way to plot this point is just to look at the entropy value and place that relative to the other entropy values that we have. So we found this to be 0.34385, which is just slightly greater than this S3 value. So we're just going to move a little bit to the right along this entropy axis here. So maybe we'll be just right around here. And then again, we'll be along this line for this saturation region. So we'll be right around here at state 4. And then this is going to be here, S4 is equal to 0.34385. Sorry, it's getting a little bit bunched up there. So these are all of our points. So now we just need to connect them. So we know that the processes from 2 to 3 and from 4 back to 1 are both constant pressure processes because we're not changing in pressure here and we're not changing in pressure from here to here, which means that we just go along our isobar lines from 2 to 3 and from 4 to 1. So let's draw in those connections now because we're just going to go along those lines. So from 2 to 3, we just trace along the line and we'll have an arrow pointing from 2 to 3. And the same is true for 4 to 1. We will follow along this line like that. From 3 to 4, we'll just have a pretty much linear line because we're not really changing that much. If you want, you would maybe curve it a little bit down into to the right like that. But we're not changing in entropy that much, so it's mostly linear. And then from 1 to 2, we'll just have a curved line kind of like this. That's just how our lines usually look up here. And so this is what our line will look like from 1 to 2. So this is our final TS diagram. Again, we had to find some of the information for the entropy and temperature values. And then we plot all of our points, making sure that we know what phase we are in at each point, and then just draw the lines to connect them.